All right, today we're going to tackle a concept that's, well, it's both incredibly elegant and seriously mind-bending, the Y Combinator. It's one of those foundational ideas in computer science that shows us how something we use all the time, recursion, can actually be built from the most basic parts imaginable. So let's dive right in. So we're all pretty familiar with the basic idea of recursion, right? A function has a name, and it can use that name to call itself to solve a problem, like, say, calculating a factorial. It refers back to its own logic to get the job done. Simple enough.
But here's where things get interesting. Here's the twist. What if a function had no name? Or what if it was forbidden from using its own name within its definition? How could it possibly call itself if it doesn't even know what it's called? This is the core puzzle we're going to solve today.
Now, this isn't just some abstract brain teaser. It's a very real constraint in some of the most fundamental systems of computation, like lambda calculus. I mean, we're talking about a super simple, super pure model of what programming even is.
And that's the rule, plain and simple. You just can't write a function and have its own name show up inside its body. So that means direct recursion is completely off the table. This forces us to find a totally different and, frankly, a way cleverer method to get the same result.
Well, the solution actually comes from this really beautiful idea in mathematics. Instead of trying to make a function call itself by name, we're going to find a special value for that function. A value that, when you plug it into the function just spits that same value right back out. It doesn't change it. That's what we call a fixed point.
And the tool we use to find this special value is called a fixed point combinator. Just look at that equation on the screen, because that's where the magic happens. You see how fix f on the left is the exact same thing that's being passed into f on the right? That, my friends, is recursion. We just kind of snuck it in through the back door.
Think of it like this. The Combinator is on a mission to find a version of the function that's perfectly settled. It finds a point where applying the function's logic to it doesn't change it anymore. It's stable. It's the final, complete, recursive function we were trying to build in the first place.
So, what is this magical tool? Now, here's the thing. There are actually an infinite number of these fixed-point combinators out there. But the most famous one, the one that's basically a monument in theoretical computer science, is Haskell-Curry's paradoxical Y Combinator.
And there it is. Yeah, I know. It looks like a bunch of random symbols, right? Super intimidating. But here's the secret. You don't actually need to trace every little lambda and parentheses. What's really important is understanding what this elegant little piece of code does. And this quote just hits the nail on the head. It perfectly illustrates its power. The Y Combinator proves that recursion isn't some special feature a language has to give you. Nope, it proves it's a fundamental property of computation itself, something you can build from the ground up, using the absolute simplest building blocks.
Okay, let's try an analogy. Picture the Y Combinator as a kind of function factory. You hand it a really simple blueprint. That's our non-recursive function template. It just knows one step of the logic. The Y Combinator then takes that blueprint, does all the complicated wiring for you, and boom, it hands you back a brand new, fully working, recursive function. It's literally the machine that builds recursion. All right, let's make this real. Enough with the theory. We'll use a classic example, the factorial function. How on earth are we going to calculate 5 factorial if our function can't even say its own name? So first, we make what's called a template. This template knows the basic logic. If the number is 0, the answer is 1. Otherwise, multiply the number by whatever comes next. It's basically sitting there with its hand out, waiting for some other function to tell it what to do for the recursive part. And that's our cue. We feed this template into our Y Combinator factory. The Y Combinator takes that empty slot for the recursive call and cleverly wires it back to the function itself, producing a new, complete factorial function. And just like that, the puzzle is solved. Okay, so this is obviously a really clever idea, but that begs the question, right? If this thing is so powerful, why aren't we all using it in our day-to-day coding? Let's talk about that gap between the beautiful theory and, practical programming.
So on one side, the Y Combinator is this huge, profound theoretical achievement. It proves recursion is fundamental. It's a cornerstone of how we even design programming languages. But on the other side, in the real world, it's just not practical. It's way less efficient than the recursion that's already built into modern languages. In fact, in a lot of them, trying to run this would just crash your program with a Stack Overflow. We just have simpler, more direct ways to do this stuff now.
And that's really the bottom line for any of us who are actually writing code. The Y Combinator isn't a tool you pull out to solve a problem. It's a concept you keep in your back pocket to understand at a really deep level what computation is all about and what's possible from first principles.
And just when you thought it couldn't get any weirder, here's one last mind-blowing fact for you. The Y Combinator? It's not the only one, not by a long shot. In the wild world of lambda calculus, there are literally an infinite number of different functions that can do this exact same job. The Y Combinator is just the most famous one, the rock star of the group.
So what the Y Combinator really teaches us is that something we think of as a core feature, like recursion, isn't magic. It's not handed down from on high. It can be built from scratch from the simplest parts imaginable. And that leaves us with a really big question to chew on. If we can build recursion from nothing, what other essential programming features that we use every single day, things like loops, data structures, maybe even object-oriented programming, are just clever combinations of even simpler ideas just waiting for someone to figure out the recipe?